All right, welcome. So this is for Physics 2710. It's our first video with the outbreak of the coronavirus. So it'll be a little different for us. So hopefully we can adapt and get used to this format. I actually thought we would start with an example that we already solved before. And I thought it's an easy one, and I thought it would kind of help get things rolling. So I thought my plan here is for the first few videos just to go through simple shapes and calculate the electric potential. And then we'll kind of branch out and start talking about capacitance and then current and resistance and circuits. So that's kind of the plan over the next few videos. So anyways, let's get into this. All right, so the scenario I have in mind here is a ring centered maybe in the XY plane, and then at a point along the Z-axis above the center of the ring, we're going to calculate the electric potential. All right, so let's draw a picture of that. So I'm going to make sure I'm spaced right. So let's imagine we have a ring, and we're going to have a point up here at a distance Z along the center of the ring. And let's go ahead and let the ring have a radius R. Excuse me. Because it's a ring so the charge is going to be spread over this ring at a constant radius. Personally, when I have these constant parameters, I like to make those capitals just so visually I know what's variable and what's constant. Okay, so we have charges spread over this ring. And if you think about it, a ring is a one-dimensional shape because you can parameterize your location along the ring by specifying one quantity, one number, namely the angle. So if you know the angle, you know immediately the place along the ring. Okay, so that's fine. So we have theta, it's going to run around the ring. It's going to run from 0 to 2 pi. We have charge spread all along that ring. So we have charge kind of spread all along that ring, that one-dimensional shape. And we're wanting to know what is the electric potential up at the top. So if you think about it, as we always have in electricity and magnetism, you have to break the phenomena into the effect of the sources of the effect, and the charge or the receiver or the observer, the thing which will observe the phenomena. Okay, so in this case, we are trying to find the electric potential created by the ring, so that's the source, and the observer, the would-be observer, would be up here at position C. There's no true observer in this problem, but we know how to handle that if one came along. So the charges that we care about for the sources are here. They're all spread all around. So what I should imagine is this ring is broken up into little point charges spread all around this circle. And what we're going to do is write down the formula for the electric potential that each one contributes, and then add them all up using calculus. All right, to do this, let's first remember that we have to, well, let's write out how that would go. So the formula would be each little teeny tiny bit has a charge dq, and the formula then for the electric potential it would generate is dq over, and there's always a 4 pi epsilon naught, times a 1 over the distance from each little bit of source up to the place where you're making the observation, or you might make an observation. So that's the vector from the source to the observer. And for the electric potential, we only have the first power, and because it's a scalar quantity, there's no unit vector there. It's very similar to what we had for electric fields, but a little different, as is appropriate. Okay, so that was for one little bit of charge, and then we have to do the same thing for many different bits of charge, so we have to integrate it. So we arrive at a very reasonable formula. This is typically what you get for distributed charges. And we made one other little assumption. When I wrote out the potential, the electric potential for a point charge, there could have been a constant, but we chose the constant so that the potential would vanish at infinity. So we've grounded the place at the, there's sort of a ring or sphere infinitely far apart, and we've grounded that place and said that that would have zero potential, and we measure everything relative to that. Okay, so this is a perfectly good physics formula. But if you hand this to a mathematician, they'd say, eh. So what is that? So we have to mathematize this physics. So if we just have these string of symbols, we have to interpret them all as appropriate for this situation. So dq, that's just a baby-sized piece of charge associated with a baby-sized piece of length. So I can write dq as lambda, the charge density, times ds, be the arc length around that ring. That's nothing other than lambda times r d theta, using the arc length formula for a ring. Okay, that was easy. Now let's go through the position vector for the source. Well, there are many of them, so we just pick a generic one, and then we're going to write things in a way that we can kind of integrate it up. It's going to be, now there are a couple ways that we could write this. We could write it as r in the radial unit vector direction in the plane. And that's not a bad way to do it, except you have to remember that this radial unit vector is not a constant unit vector. It depends upon the angle. So as you go around the circle, or the ring, r vector changes. So maybe, excuse me, I apologize. Excuse me. So you could also write that as r times, we can write that as cosine theta x hat plus sine theta y hat. Both are perfectly adequate. This makes the angular dependence manifest. This just looks nice and compact. Okay, and then, so that's the position vector. Say out to, let's say I wanted to focus on this piece of charge. This would be rs. It's a vector that points from the origin out to a little bit of charge. Similarly, I can coordinatize, or I can turn the position of the observation point, RO, into a vector and write that as z times z hat, where z hat is the vector runs in the vertical direction. So I'm saying x and y are side to side, and this is in the z direction. No problem. Looking up at where I want to end up, I need to work out what is RSO. So I'm going to write RSO, so that's going to be RO minus RS, which is simply z hat, and I'm going to go with the compact notation, minus r hat. And remember, r hat would point in the plane, z hat is up there, so they're perpendicular, so their dot product would be 0. Okay, and I can tell then, really I can even just tell from this picture, that the magnitude of, this would be RSO, points from S to RO, to the observation point, the magnitude of that is simply going to be capital R squared plus Z squared. Or you can take the dot product of RSO with itself and work out the magnitude. Either way, we get magnitude RSO is simply the square root of R squared plus Z squared. Nice. So we have turned this kind of formal, this abstract physics formula into something you could hand off to a mathematician and they would know how to interpret the symbols. So this simply becomes, plugging all this in, lambda we will take to be a constant, so we pull it out. 4 pi epsilon naught pulls out. Okay. We're going to pull out, so the magnitude of RSO is a constant because as you go around this circle, it never varies. So that just pulls out, is 1 over the square root of R squared plus Z squared. And then I have, what's left is the integral. dq gives me a, so there's a factor of R, I forgot that. R. And then I have d theta, integral d theta from 0 to 2 pi. And I arrive at the final formula, which is, separating all this out, that the potential due to a ring at position 0, 0, Z along the center of the ring equals, well, I get a factor of 2 pi from this integral, and I combine that with lambda and R, and I get 2 pi R lambda over 4 pi epsilon naught square root of R squared plus Z squared, which is the same as Q, just 2 pi R lambda would be the total charge, over 4 pi epsilon naught square root of R squared plus Z squared. And that's a nice formula to have. Remember, on a test, I would expect you could derive this if needed. So it's not enough just to memorize the formula, but that's a kind of a nice, convenient formula. It's particularly nice because you can imagine taking a limit as Z ran all the way off to infinity, in which case this would become Q over 4 pi epsilon naught times 1 over Z. It looks like a point charge. If you're infinitely far away from the ring, it looks like a point charge. And that's a very reasonable result. Okay, so next up, we're going to find the electric potential of a disk of charge.